last week we had seen how to design a proportional temperature controller. This week we will see how to design a PID temperature controller. So, PID temperature controller is actually gives much better performance than proportional controller. This is extensively used, and we should understand why this intercurrent action. PI means proportional intercurrent temperature controller. We also will see later what is proportional intercurrent differential temperature controller. So, in proportional temperature controller we had seen that we had what we had done was we had the actual temperature here, and then we had the set temperature which is minus voltage. So, that is given a reverse of the set temperature. So, the difference was we got the difference between set temperature and the actual temperature. This difference is called error voltage. Error voltage is amplified and then given to the heater. Error voltage was amplified by gain times, and then that was driving the heater. This is what we have done for the proportional controller. The problem here was one, the set temperature is not equal to actual temperature. So, if you set at 70 degree, you will not get 70 degree stabilized oven, but you will get little less than 70 degree. The difference actually depends upon how much gain that you had given. So, essentially the error voltage, error into the gain is the heater voltage. Since always we need a heater voltage and the gain is not infinity, so always there is a error. So, but if you increase the gain, then error will come down, but then you might have seen that if you increase the gain, then the system trying to oscillate, and then this creates a problem. So, first we see how to reduce this errors, because if the error is not there, then there is no problem, we can reduce the gain, and oscillation also will not be there. So, how to reduce this error voltage? That is where the proportional plus intercurrent controller comes into picture, and this is a really great invention. It was invented by the practicing engineers practically implementing this in many control systems. So, the PI controller looks like this. So, you have say temperature sensor. This is similar to what we had here. For example, I can have a LM335 as a temperature sensor. Then I can also have reference voltage. So, you can have a reference voltage. So, we can have a reference voltage. So, reference voltage, what we do is we give a minus, so that it is easy to get the error difference. So, what we do is we set the temperature here and find the difference between these two. It is similar to what we have done with proportional temperature controller. So, what we do is we find the difference between these two. So, I will find the difference between these two. So, you will get the error voltage here, that is the difference between the set voltage and the set temperature and the actual temperature. So, this is a Zener voltage, Zener. So, we fix the set temperature is here. So, when temperature goes up, in this case this voltage will be increasing by 10 millivolt per degree C, and then since this is plus, this will be going in the minus side. So, when temperature increases, you will be seeing that the minus voltage is increasing. If you want actually plus, we can also change it, or we can invert it, or we can since it is a error voltage, we have to amplify and then add it. So, what we can do is we can if you want we can invert it, so that it becomes plus. So, essentially when temperature goes up, more plus voltage is coming here, and that makes this one go minus and this one go plus. So, you will get when temperature goes up, essentially this voltage will be increasing. What you do is this we give it to a proportional stage, then also we give it to the so called integrated stage. So, here what you do is we will just connect the integrator. Now, what we do is we sum these two voltages. Here actually I sum it, and this I can add to this. So, essentially you are adding the integral output and the proportional gain. This gives you the gain. So, this is the error voltage. So, when temperature goes up, this increases, then correspondingly this amplified and it will be going minus, and that will be inverted and you will get a plus. And then whenever error is there, this slowly charge up the capacitor, and this voltage also will go towards minus, and that will become plus. So, you will get addition of addition of this voltage and this voltage at this point. So, the both are summed up, and the summed up voltage is available at this point. So, essentially the error voltage is amplified, and the amplified voltage appears here. The error voltage is time integrated, and the time integrated voltage is available here, and that is summed up with this proportional this amplified error voltage and summed up with this, and then you get a total voltage at this point, that is sum of P and I will be appearing here. This we can use it to drive the heater. So, the heater can be driven through the our standard we can have our for example, we can have plus 15, and then I can have a heater here. So, that is a heater voltage, a heater. So, this is the circuit diagram of a PID temperature controller. Now, we have to see this carefully in at another angle, how this avoids, how this removes the error voltage, because once if you put this integral stage, eventually what happens is you will find if you set at 80 degree, the temperature also stabilizes exactly 80 degree, you will find there is no error at all. How that is achieved? Now, to understand this, we have to see first what happens if I remove the integrator. Now, if I remove, for example, I remove the integrator from here, I removed. Now, this is just a proportional controller, because the difference in temperature at this point gives you error, and that error voltage simply amplified here, and that is inverted and comes here and drives the heater. Now, if I set at say here 70 degree, you will find that temperature is not stabilizing at 70, it will be at 68 degree. Now, we see what happens if I add this integral stage. So, I put the integral stage here. Now, if there is a output voltage here error, that actually will be adding up slowly, it is a capacitor is here and the resistance is here. So, whatever voltage is here, it will be this is 0. So, this is 0. So, there will be a current through this. So, the current through this will be the error voltage divided by R. So, the same current goes here and charges up the capacitor. So, eventually this voltage will be slowly going towards minus at the rate determined by this current, because I into T is equal to C into V. So, the I, that is nothing but error divided by R. So, with the time, then C is fixed. So, with the time, as time increases, we have to increase. So, only thing is it is minus, but that at this point it can become plus if I give it to this inverter stage in addition to what is coming from the proportional stage. So, what I do is I will put these values equal, all 3 equal, then whatever voltage is here that will be added with whatever voltage is here, that will be added with this voltage, and that will appear here. But what happens initially, morning when you switch on the system, you will find that you had set this one at 70 degree, and the heater was only because this is anyway linked to this one. So, this is at 25 degree. So, eventually you will have a output voltage as output voltage will be, the error voltage will be high, and this is having a gain, because we do not keep this one 1:1, we keep this one. For example, I will put here 100k and 1k, that means I am giving a 100 gain per proportional stage. So, you will have a high voltage here, and that this is anyway minus, and that becomes plus, and the heater will be driving. At that time this voltage was initially, the inductor, the capacitor was not charged. So, you will have almost 0 voltage, but with since error is there, it will be slowly started increasing towards minus side, and that will be, move towards plus side. So, what happens if it is already saturated, there will not be any change, but as this increases, this voltage also supposed to increase if it is not saturated. Even if it is saturated, there is no harm. Then after some time this temperature of this would have increased, then the error voltage will come lower, and this also would have reduced. By the time this would have achieved enough voltage, and you will got now contribution from this as well as from this. After some time, suppose the error had become 0, the set temperature exactly equal to set temperature equal to the actual temperature, then error can become 0, and you will find no output due to this, and this becomes 0. Then this also becomes 0, but that makes no current flowing through this, but whatever charge that was stored earlier on this capacitor will remain there, and the output voltage will remain there even though the error voltage is 0. That is the actual advantage of this integrator. So, you have the input 0, but output voltage is still there because the capacitor is already charged. So, you have this output voltage that now will be driving the heater. Now, that is what we wanted, because with the error we need some output voltage to the heater, because heater voltage cannot be 0. If it is 0, then there will not be any heating. If there is no heating, and it cannot stay above ambient temperature. So, that means we able to get the heater voltage without having any error. Suppose you may ask what happens if the temperature had gone higher than the set value. Suppose if the temperature goes higher than the set value, the error becomes minus, then the minus makes the reverse current flow, that means the capacitor will discharge and the voltage will reduce, and this voltage also will reduce, and anyway this minus actually become plus, and this plus again become minus. So, that again reduces this voltage. So, even if the capacitor will discharge only if the temperature exceeds the set value. So, again if in case if the voltage drops too low, then it does not matter. If the temperature comes down, again the error voltage will come, and then you will see that this is again charging up, and the heater voltage also again increasing. This way the integrator makes sure that there is no error at all, in the sense that set temperature will be exactly equal to actual temperature. This is good, because if we add the difference, that if there is an error, we are seeing that this produces a secondary effect, in the sense that if the ambient temperature changes, then the error also changes, and that creates a problem. It appears as if the controller is slowly drifting with the ambient temperature. This problem is solved by adding a integrator. So, the integrator was a good invention, but then always we get confused, because integrator is there. Of course, I can reduce the gain substantially, because even if the gain is lower, the error not going to be there at all, because integral action is there, that will take care. But one have to set correctly the required gain, and then the required time constant for the integrator. Now, this is a issue that is to be discussed in detail, because one may wonder why when the gain is high the system gets into oscillation. This actually we have to pick up this this information from our established control theory, because what happens is in any control system we have to see what is the electrical equivalent of a control system, or in this case electrical equivalent of this temperature controller. Now, I can show the electrical equivalent like this, that you have a system on RC, then I have another RC, say R1 C1, R2 C2. Now, I put here the system with some gain G with the reference V reference. This is where we want to set the temperature, and this I give it to back to this. Consider a system like this. Here we are model this R1 C1 as the equivalent time constant of the oven. For example, if I apply a voltage to the heater, then the temperature of the oven slowly rises. Same thing happens here. I apply voltage here, then voltage at this point slowly rises depending upon the time constant of this. So, we take this is a time constant of the system, equivalent time constant of the system. Now, take R2C2. R2C2 actually represents the time constant of the sensor, because if this is the time constant of the sensor. So, now actually what we have done is we have modeled system and the sensor into the control loop using low pass filter, that is R and C. We have realized the time constant of the system and time constant of the sensor. So, if I put, for example, if I take a temperature sensor, the time constant of the sensor is roughly equal to 1 second. That is, I can always make it this RC time constant as 1 second. Similarly, this is the time constant of the oven. It may be 100 seconds or 200 seconds, that depends upon the system. Now, consider this case. Here we have a oven and here we have a temperature sensor, and then what we are doing is temperature sensor output we are given to the comparator or an amplifier, and then we are compare it with the reference. This is a set value. The difference between these two is amplified, and amplifier voltage appears here. Now, if I have a system like this, naturally this will oscillate, because when if I increase this, then increase takes place with the time delay, and even this voltage whatever is there in the oven that is sensed only after again some time delay given by the time delay of the sensor. Because of that what happens, that by the time it reaches the actual temperature, the voltage here had already gone much higher, and net result is the system will be keep oscillating many times. Now, if the gain is sufficiently large here, of course, if the gain is less, it will not oscillate. Now, to understand that, we can look this in the whole system in a slightly different angle. For example, if I take RC, this RC can give a phase shift as much as 90 degree, and this RC also can give a phase shift of 90 degree at some frequency. If at some frequency, if this phase shift also 90 degree and this phase shift also 90 degree, then total phase shift introduced by this and introduced by this will be equal to 180 degree, and we have this controller is already having 180 degree phase shift. That means, at some frequency it is possible to have a gain of 360 degree, a phase shift, total phase shift of 360 degree, because 90 plus 90 plus 180 can give the phase shift of 360 degree. That means, we got a phase shift of 360 degree, that is one condition required for the oscillator to work. So, we already produce a 360 degree phase shift. Then another condition satisfied for the system to oscillate is the loop gain should be more than 1, because we had given a gain here, some gain in this, but then these two are actually acting as attenuators, because if I give some frequency here and some say some frequency some AC signal of some frequency say 1 volt amplitude, then at this point I will have only reduced voltage. That means the system works as attenuator here, and this also works as attenuator. So, attenuation provided by this and attenuation provided by this, the combined attenuation, if it is combined attenuation into this gain if I take, and if it is more than 1, and if the phase shift is as I said is the entire loop phase shift is 360 degree, then the loop can oscillate. So, if you do not want the loop to oscillate, we have to make sure either the phase shift is not 360 degree around the loop, or the gain is lower than what is attenuation provided by these two RC elements. If that is satisfied, then system cannot oscillate. So, we know that RC time constant it is a single pole filter, and this also single pole filter. So, above fold frequency, the attenuation provided by this is 20 dB per decade. That is, it attenuation linearly linearly increases with frequency. This attenuation also linearly increases with frequency. For example, if I take the pole frequency of this, the pole frequency is we call 1 f equal 1 by 2 pi RC, that is the pole frequency. If the pole frequency say for example is 1 kilohertz, that means at 1 kilohertz it will give you 45 degree phase shift. Then at 10 times the pole frequency, say at 10 kilohertz, the phase shift will become 90 degree, because if we plot the phase shift versus frequency, say theta versus frequency, that actually it is almost 0 degree phase shift, and then at pole frequency it becomes 45 degree, that is at Fp it is 45 degree. Then 10 times the pole frequency, this actually becomes 90 degree. Then afterwards it almost stays there, stabilizes there. So, 10 times the pole frequency you will get 10 Fp, the phase shift is 90 degree. And we also know that at pole frequency you will have the attenuation provided by the filter will be root 2 times, that is if it is 1 volt you will get 0.7 volt at pole frequency, and at 10 times the pole frequency, if it is 1 volt you will get only 0.1 volt, because the amplitude also is given by the relation, the output amplitude actually is goes by again the ratio of this f by fp. So, if the pole frequency, if the actual frequency is 10 times more than the pole frequency, then attenuation will be by a factor of 10. That means, if it is if the as you increase the frequency, the phase shift is increasing, but the attenuation also increasing correspondingly. But then we know that sensor is having a very low time constant, say 1 second, and this is say is having a time constant of about say in this case 100, and normally the sensor, this system time constant is high, and it is a must, because if system constant is not high, we will show you that it is very difficult to give higher gain. So, now the question comes, if I have a system like this, having understood like how the attenuation is taking place here and then here, and then how the loop phase shift is coming around, now we should try to find out what is the condition that you need to avoid the system to oscillate, that is any one of the conditions should not get satisfied if you want if you do not want the oscillation, in the sense that either the phase shift should not be 360 degree around the loop, or the gain should be less than 1 around the loop. If if any one of them should be there, if satisfied, then the system will not oscillate. Of course, one easy way is reduce the gain. If you reduce the gain, then attenuation will be dominating, and then the loop will not oscillate. That would be that can be done very easily. Now, you can work out and see. I will show you that if the system, if the gain, the for example, I find the system time constant, divided by sensor time constant. I find the ratio between these two. When the ratio between these two, that that should be always less than the gain, in the sense that sorry, it should be other way around, that is the that gain should be smaller compared to this time constant. For example, if it is this system time constant is 100 and then sensor time constant is 1 second, if this 100 seconds is 1 second, then the gain should be less than 100, then system will not oscillate. This you can work out and see, because if this is the case, you will find that condition for oscillation will not get satisfied in terms of the loop gain. So, if one maintains this ratio, that is the gain of the gain of this amplifier, if it is less than 100, then definitely system will not oscillate at any frequency in this case. That means I had to make sure that system the overall the gain given the actual gain given by the error amplifier is less than 100, then it will not oscillate. So, in our PI control, what we have discussed just now, what we have to do is I have to set the gain here, I have to set the gain that is the gain here, what we have shown here is 100. This gain must be lower than 100, that is that 100 is coming because of the ratio between the system time system time constant and the sensor time constant, and if this gain is less than 100, then the system will not oscillate. So, normally what is done is we keep about 50% margin. So, if we need gain of 100, we keep gain of 50, then per proportional action, then the system will not oscillate. Then now we add the integral time constant. If we add integral time constant, then since the gain is less, if PA proportional action alone was there, you would have got a lot of error. Because of integral action, now the error also goes off and the system stabilizes without any oscillation. So, the gain should be set correctly like that. Now, the one more question comes into picture, that there is a difference between electronic gain and the system gain what we have discussed, because in the system what we had shown here it is actually a temperature system. So, all the units must be in terms of temperature. So, the gain that we get what we set also has to be in terms of temperature. This is a little complicated issue. Many of the textbooks actually ignored this and then they create a continuing doubt in the minds of students ever. What we have to understand is that, for example, if here the system time constant is 100 and sensor time constant is 1 and the gain required is not more than 100, and if I put here 100 gain, you will find the system is not working properly, because the gain 100 what we are told there is a temperature gain, not the electronic gain. So, we had convert this temperature gain into electronic gain, that is a must. So, how to convert this temperature gain into electronic gain? So, we will see how to do this, because this is very often ignored and then we will end up in blaming the temperature controller. So, we should find out how to convert temperature gain to into electronic gain. Now, for this we had asked the question, suppose if I have a heater, how much voltage I had to give to raise the temperature of the oven by 1 degree. For example, if I take a system like this, assume this is the system and this is a heater which was connected in our case to 15 volt. So, one end was connected and another end was connected to the heater driver through Darlington we have connected like this. Now, if I vary 1 volt here, then what is the temperature rise expected here? Now, for example, 1 volt change may raise the temperature of this, assume in this case the temperature goes up and stabilizes. For example, originally it is say 5 volt, then temperature at this point was say 50 degree, then I give 6 volt, then temperature will go little higher than this and stabilize, because assume that it is 55 degree. That means, for every 1 volt, that is at 55 degree it went and stabilized, but at 55 degree what the heat coming in is equal to heat going out. That means 1 volt change here gives you 5 volt 5 degree temperature change. That means 1 volt in heater, 1 volt heater voltage equal to 5 degree temperature, 5 degree temperature rise. Then that means if I get 1 volt at the heater, then it is equal to telling I am having 5 degree temperature rise. Now, 1 degree temperature rise gives here 1 degree temperature rise gives us 10 millivolt output from the sensor. Output from the sensor. That means, if 1 degree change occurs, then I will have 10 millivolt change in the error voltage, because if you go back our circuit and see, 1 degree change here will give us 10 millivolt change here. Now, 10 millivolt change, if the temperature gain is supposed to be 100, because we want a temperature gain 100, that means 1 degree change in temperature should produce voltage change here corresponding to 100 degree. That means 1 degree change should give me here 20 volt change, because 1 degree 1 voltage change here we have said is producing 5 degree temperature change. That means, to change 100 degree temperature here, I need to have 20 volt change here. That means, if at this point if 20 volt change occurs, we know that the temperature will change by 100 degree C. That is, we had find out experimentally, there is no other go. So, if that means, if 100 degree change have to occur, then 20 volt change have to take place here. That means, 20 volt change have to take place with 10 millivolt change here. So, what actually works out is 10 millivolt change should produce 20 volt change at the heater. Because 20 volt change at the heater will change 100 degree temperature change, but we know 1 volt change, 1 degree change will give us 10 millivolt by this sensor. That means, if I want 100 gain for the temperature gain of 100, then 1 degree change should produce a 100 degree change, voltage change corresponding to 100 degree change. That means, 10 millivolt change should produce 20 volt change. This works out 2000 gain. So, that means, electronic gain required is 2000. So, if you work out this, that means the electronic gain, required electronic gain is that is 20 volt divided by 10 millivolt, that is equal to 2000. Essentially speaking, temperature gain of 100 is equal to electronic gain of 2000. So, I have to have the gain setting to be done, that is the resistance change, the resistance what I have to set here is not 1 and 100 K, I had to make it for example 2000 gain here, I should put 1K and 2000 K, that is a 2 meg. If I want, I can put this one in 2 stages, which we see later how to get large gain. Instead of getting large gain one single stage, it is better to get large gain in more than one stage, that gives a better result. This we see later, but what is required is electronic gain requirement is 2000. So, once you do that, then the system will stabilize without getting into oscillation. Actually what you need is gain of less than 2000 is required. So, what actually done is not this one, we have to put in this case 2000 K, sorry. So, 2000 K, that will give you 2000 electronic gain, and that will correspond to 100 gain of temperature. Same thing, same type of scaling to be done even for this intercalator time constant setting also, because the voltage levels are different. So, if you had to set the intercalator time constant, we also had to set only in terms of temperature unit, not in terms of electronic unit. This I leave it to you to think for some time till my next class comes, because next class I will explain you how will you do this, because you can work out and see mentally, you can think how to convert this time constant electronic time constant from the temperature time constant that we are expecting, because we can also show you from the control theory that the time constant of this integrator should be equal to system time constant if you do not want system to oscillate. That means, I had to put RC is equivalent to system time constant. In this case, it is supposed to be 100 seconds, but 100 second means we had to also consider same type of scaling that we had used in the case of temperature. So, one can set this R and C after scaling, then only it will work. I will not explain in this class, I will explain how to do this in the next class, because this kind of scaling is not done invariably, and it is not it is a ignored one in almost all the textbooks done, and then invariably you find when you design the controller it gets into a lot of oscillation, and then a lot of trial and error is done, and then we try to use this. Now, we see how can we add a differentiator, and what is the necessity to add a differentiator to make it a PID temperature controller, because PID temperature controller is the workhorse in the industry. So, it is essential we try to understand how to make a PID temperature controller. So, what I do is that we now see how to make a proportional integral differential. So, the so called PID temperature controller. Now, what can be done is we can use the same logic, just add the differentiator stage, then this becomes a PID temperature controller. Let me read quickly the entire circuit. So, what we had done was, we had in the earlier case we had our temperature sensor that was given to I think it was given to plus 15, then LM335, then we had minus 15 as a reference voltage, that is a set value. Then we had the difference between these two. The set value, the error between the set value and the actual value you have got here. So, that is the error voltage, and then in earlier case, when the temperature goes up, this is plus is going up, and then this will be going minus. So, to remove that, we are inverted this. So, that also can be done. Now, you got a error voltage here. So, when temperature goes up, this also will be going up. Then we add proportional all three stages here, that is PID stage, the first proportional stage. So, I set the electronic required electronic gain here, then I add the let me add the integral action here, integrator. So, that error voltage drives this. Now, I add differentiator here. So, we add a differentiator. What you do is we put the capacitor here, then the resistance here. So, you got a proportional stage here, the integral stage here, differentiator stage here. So, these three are you have done it. Then you sum all these three, like earlier you had integrated summed only P and I, now we sum all these three. So, you got the summed up voltage that should drive the heater now, that heater drive can be put now. And then connect the heater. So, you have a heater here. Of course, this heater is actually physically coupled to the sensor here. This is physically kept here. This is driving the oven, and that sensor is connected here. So, that it acts as a temperature controller, because that feedback automatically takes as temperature sensing is done. That is how the feedback is taking place, and then the system will try to stabilize at the set value. That is the aim of this PID controller. So, if we see our earlier discussions, that we had a proportional controller wherein we had only this stage and these two were not there. Then we had added for proportional integral action, that time we had only these two and this was not there. Now, we had a differentiator stage added here in addition to this, then it become a PID temperature controller. All these outputs are summed up at this point to produce the net voltage, and that is the one which drives the heater. Now, the question comes, why you need a differentiator? Because earlier we said we need an integrator because proportional controller alone, if it is there, it is having error voltage. If there is a error voltage, then system is not stabilizing at the set value. So, we said we will add an integrator. By adding integrator, we have removed the error voltage. So, even if you give a low gain also, there is no problem, because error is not there. If error is not there, then if ambient temperature changes, it will not make the system to drift, which we have already explained. So, proportional integral action is enough to get a good stability. If the system oscillates, all that we can do is we can reduce the gain. So, that if the gain is less, then system not going to oscillate, that we have explained, because we explained earlier by showing what is the necessary condition for the system to oscillate. So, once that is not satisfied, once that not system will not oscillate, that we can achieve by reducing the gain of the proportional stage. So, it looks as if proportional integral temperature controller is enough, and there is no reason why one had to go for differentiator. The requirement of differentiator comes depending upon the speed of the response. Now, there are two issues which are coming. Now, by adding a integrator, what happened? We have removed the error, but then the system, the integral time constant is kept equal to system time constant. Because of that, what happens? The output of the integrator changes very slowly only, and we already reduced the proportional gain to avoid oscillation. So, the output for the proportional stage also low only. So, to get a enough voltage for the heater to rise, we have to wait for quite a long time, because this is works only very slowly. Probably for a system like temperature controller, you do not need a differentiator, but there may be a case we are controlling a faster system. For example, we are controlling a position using a position of a mechanical system using a motor. in that case if I want to control the position instead of temperature, then I will give a voltage corresponding to position here, and then I will get a position feedback, and then probably I will make an arrangement to drive a motor in this case. In that case what happens, if the differentiator varies slowly, then system become very sluggish, the system will not go to a set value quickly, and then it will take long time. So to avoid that, it is essential that we have a differentiator. This makes the system very fast. Then there is another advantage with the differentiator. Suppose if I make the differentiator time constant is equal to one of the time constant which we had discussed, because we said this temperature control system is having two time constant, one is system time constant, another one is a sensor time constant. Assume that I make the sensor time constant equal to differentiator time constant. If these two time constants are matched, then for the system it appears as if only one time constant is there, that is system time constant alone is there, and the other time constant is cancelled by this. That is good, because if I have only one time constant in the system or only one delay in the system, then maximum phase shift that you can get would be only 90 degree. Because one RC can produce only 90 degree phase shift, not more than that. With 90 degree phase shift, system will not oscillate even if the gain is higher, and that is good for us because we do not want the system to oscillate. So it is always advantageous adding a differentiator, and that too if I match the differentiator to one of the time constant, even one pole also get cancelled, and oscillation of the system can be avoided. So differentiator may gives us two advantage. One is it makes the system fast, other one is the one if I match it to one pole, then the system oscillation also can go away. So what we do is we match this one of the time constant. Before that, let us try to understand what is the how the electronically the differentiator works, and what really happens to what really makes this the differentiator is a ideal element in this case, because many times we will use only P and D is enough, even integrator is not necessary if I can give large gain to the system, because I can increase the system gain if I add D, because I remove one pole. If with only one pole, system will not oscillate even if I give a high gain. So let us try to understand how the system works. For example, if the temperature error voltage change, for example, the error voltage increases here, we will see the increase in voltage will produce a changing voltage at this point. What is the change in voltage? Because this is capacitor C we have here, so this is R. So current through the capacitor is C into dV by dt. That is the current through the capacitor. So voltage at the output will be C into dV by dt into R. So that becomes CR into dV by dt. So where dV by dt is the rate of change of this voltage, or rate of change of actually the temperature here. So temperature change produce a voltage change here, and the voltage that is available at this point depends upon the rate of change. So if the temperature change is fast, or if it is a mechanical system where I am dealing with positioning, then if the system is moving fast, then this voltage also will be changing fast. That will produce a large change in voltage, because if dV by dt is more, you will get large voltage change, and large voltage change will occur here, and large voltage change occur on the system. That means if the system is faster, then correction also taking place faster, or other way around, if the error is changing fast, then correction also changing fast, and system will stabilize quickly. So that way the differentiator helps us for system to stabilize fast, and invariably we match the differentiator time constant equal to sensor time constant, because sensor time constant will be the slowest, sensor time constant will be the lowest, because normally we try to make a sensor which is fast responding, because fast responding is required, then only we get large ratio between system time constant and temperature sensor time constant. So, normal system time constant is larger and sensor time constant is smaller. So, we try to match the smallest time constant to the differentiator. This is mainly done to avoid the noise pickup, because as I said, if the voltage change occurs here at this point, and the changing voltage produces a voltage changing voltage here. If here we are using a capacitor, and if if I have to have a large differentiator, then I have to use large C here. If large C is used, then you say C R into dV by dt is the output voltage here, and if large C is used, then even small change here will produce a large change in voltage here, and that can saturate, and we know that system is always having noise. So, if I put large C, even low frequency noise itself can produce a large voltage change here, and the system will be driven with the error only, not with the noise only, not with the error. That is not a desirable one. So, we do not want the C respond for the noise, it should respond only for the error. But any change, either it is a noise or the error, that cannot be recognized by this capacitor. So, what we do is we will take C smaller, so that the noise response is less. So, if C is smaller, the noise response is going to be smaller. So, that is why we are selecting lowest time constant for this. In addition to that, we also do one more protection, that we do not want the system to respond all the way for all the frequencies. I can make it that if there is a very low frequency change, and that actually will not produce a too large current flow, that current flow will be limited by this resistance. So, we can add a small resistance related to this R, such that we will not get too large gain for very high frequency noise, because because particularly in the temperature controller the change will be very small. Even in a normal system, whatever noise is there in the electronic system, that noise frequency will be much higher than the system error frequency. In that case, by adding this resistance, the high frequency noise will not produce a large output here, and that makes the system not noise driven, that will make the system to error driven. So, we have to have a resistance here to limit the noise response. So, that way the PID temperature controller works satisfactorily. Of course, I ask you to work out how to scale the proposed inductor time constant, and similarly the differentiator time constant to the temperature scale, because the electronic time constants, the differentiator time constant and the inductor time constant has no is the one which actually drives, but that has no relevance to the temperature time constant. So, one has to scale it up the same way as what I had shown in the example for proportional gain. Only that scaled time constant only should be used here, not the temperature time constant that you get as I had explained. So, this I can explain you later. So, mainly I am doing it so that you will think about this and then come back in the next class, so that you have some thinking to do at home. Of course, now we have to see how to make a heater drive for different systems, because here we had shown if I have a heater like this and the heater requirement is less than 15 volt, I can directly give like this and drive. But then you rarely find that you have a heater which is which needs less than 15 volt. Sometimes you may need a heater which is 1 kilowatt or 2 kilowatt or even 100 watt, 200 watt, like that. So, if the heater voltage requirement is more than 15 volt, then this circuit have to be changed. This is not enough and it will not work. For example, if you may think that many I had seen the many boys doing the same mistake. For example, if you want if the heater voltage is 100 volt, for example, if I connect the heater like this, I put a Darlington pair, connect this to ground, I connect this one to ground. Then connect the heater here. Sorry, plus 15 volt, and this is heater, and then this is our output driver, and the output of that is given to this, of course, with the series resistance. Now, if I connect like this, then this will not act as a proportional controller, because we need whatever voltage change that is occurring at this point should produce corresponding voltage change across the heater, then only the proportional controller action will work. Proportional controller is not acting well, then obviously integral and differentiator adding also will not do anything, because in this case, for example, small change in voltage here will almost produce a large change in voltage here. In fact, you have a gain here, and then you also find once the voltage goes more at this point more than 1.2 volt, you will find that it is completely switched on and will act like a on off controller, and the temperature controller action will proportional controller action will be completely lost. So, this circuit should not be used. You should not use this for PID controller or proportional controller for that matter. So, if I want heater voltage more than 100 or higher than 15, then what is that we can do? Or so what can be done is, we have to make sure the voltage change here produces linear voltage change at this point. Of course, one simplest thing that can be done is, we can add a resistance here, and then we can have a scaled resistance at the collector, or we can use this as a this voltage as a reference, and then using that as a reference we can increase the voltage and then drive the heater to a higher voltage. All these things can be done, that we will do it in the next class. I also ask you to work out some of the issues related to this, and then come prepared for the next class, because driving the heater is another essential thing that is required. So, what you do is, you can think of how to convert proportional gain, that is how to get a proportional gain from electronic proportional gain from the temperature gain. Similarly, electronic integral time constant from the temperature integral time constant. Similarly, differential time constant also to be converted to electronic time constant by scaling. So, these things you have to look at it and then come prepare for the next class. Similarly, see how to drive the heater, different heater, higher voltage heater and so on, using different circuits. These things I will explain you in the next class.